You know that feeling, right? You're using an app, maybe a website, and it just stops. For a second, it hangs. Ever wonder what's really going on under the hood? Well, today we're going to do a deep dive into the engineering that explains exactly why that happens, and more importantly, how a really clever shift in software architecture can absolutely slash those frustrating delays. We're talking about a massive performance boost. All right, so here's our game plan. First, we're going to get right to the heart of the problem, a nasty thing called tail latency. Then we'll unpack a new solution, this thread per core architecture. After that, we'll see how it was put to the test in a real-world experiment. We'll dig into the jaw-dropping results, and finally, we'll talk about what all this means for the future of building really, really fast applications. So, first things first, we need to properly introduce the villain of our story. It's this invisible force that can bring even the most powerful online services to their knees. Let's talk about the tyranny of tail latency. We've all been there. You click on something that should be instantaneous, and you get that little spinning wheel of death for just a moment. It's not your internet connection. The server is a beast. So what gives? That unexpected pause, that's the symptom. And the cause is often a bottleneck hiding in plain sight. Okay, here's the absolute key to understanding this. A modern web page isn't just one thing. When you load it, your browser might make dozens, even hundreds of tiny requests to different backend services. Now, the page can't finish loading until the very last, slowest one of those requests comes back. That slowest response time, that's the tail latency. It's the long pole in the tent, and it single-handedly dictates the user's experience. To make the whole thing faster, you have to fix that one slowest part. So, how do we attack this problem? Well, that brings us to a really powerful new architectural pattern. It's designed from the ground up to go to war with tail latency. It's called the thread per core architecture. To really get this, you have to see the difference. The old way, the traditional way, is pure chaos. Imagine you have a bunch of software threads, all fighting over a smaller number of CPU cores. The operating system is constantly stopping one thread, saving its state, loading another one, letting it run for a millisecond, then stopping it. That's called context switching, and it creates an enormous amount of overhead. The thread per core approach, on the other hand, is beautiful in its simplicity. It brings order. You pin exactly one application thread to each CPU core. That's it. Now that thread owns the core. It can run without any competition, without any interruptions. Now, there are a couple of ways to do this. One is what we call the shared everything model. Sure, every thread has its own core, but they can all still access the same pool of data in memory. This sounds flexible, right? But the problem is if two threads try to change the same piece of data at the same time, you get chaos. To prevent that, you have to use these things called synchronization locks. And suddenly, we're right back where we started, with threads waiting on each other and creating the very bottlenecks we wanted to eliminate. This brings us to the much more powerful alternative, and it's the real focus of this research, the shared nothing model. This is the holy grail. You don't just pin threads to cores. You go a step further and you partition all your data. Each thread becomes the sole, undisputed owner of its own little chunk of data. This is a game changer because it completely eliminates the need for locks. It also means each CPU's local cache becomes incredibly effective. And if one thread really needs data that another one owns, it doesn't touch the memory directly. It sends a message, kind of like an internal email, to ask for it. This enables true, unhindered parallel processing. Okay, so we've got our threads neatly pinned to their own cores. We've partitioned our data. We should be flying, right? Well, not so fast. There's another major source of disruption that can come in and wreck all of our careful planning, the network hardware itself. We have to stop the CPU from constantly distracting itself. The solution to this is a pretty cool technique called IRQ affinity. Okay, so what's an IRQ? It stands for interrupt request. Think of it like a doorbell. When a new packet of data arrives from the network card, the NIC, rings the CPU's doorbell to say, "Hey, got something for you." IRQ affinity lets us become the ultimate bouncer. We can tell the system, "Hey, I only want doorbells for network packets to be routed to these specific CPU cores." We create dedicated doorman cores that only handle network traffic, leaving our precious application cores completely isolated and free to do their real work. Because without this, look what happens. A network packet arrives. The system, in its infinite wisdom, just picks a random core to interrupt. And guess what? It's probably a core that's right in the middle of some complex calculation for our application. That one tiny interruption forces a context switch, it pollutes the CPU cache, and it stalls our application's progress. These tiny delays, happening thousands of times a second, add up, and they're a massive source of tail latency. But When we set up IRQ affinity correctly, the whole flow becomes so much cleaner. A network packet arrives, the IRQ is instantly routed to one of our dedicated network cores. That specialist core handles all the low-level packet stuff, while our application cores just keep humming along, completely oblivious and, most importantly, undisturbed. This is how you achieve true peak performance. So this all sounds fantastic in theory, right? Dedicated cores, no interruptions, but does it actually work in the real world? Does it really deliver better performance? Well, the researchers behind this paper designed a fantastic experiment to find out. To get a definitive answer, they staged a showdown. In one corner, you've got the Challenger, a system they built called Sphinx. It was designed from the ground up, from scratch, to embody all these shared nothing, thread per core principles. And in the other corner, you have the reigning champion, Memcached. It's the industry standard, it's everywhere, and it uses that more traditional shared everything architecture with locks. And they didn't just test it on one type of machine. They ran the comparison on two very different hardware setups. First, a beefy, modern server with tons of cores and a fancy network card with lots of queues. But they also tested it on a legacy setup, an older machine with fewer cores, representing the kind of hardware that's still incredibly common in data centers all over the world. This is crucial for showing if the benefits are universal. All right, let's get to the good stuff, the results, because this is where the theory smacks right into reality, and it gets really, really exciting. Let's see how this new design actually held up under intense pressure. Now, just look at this graph. This is the worst case delay, what we call the 99th percentile, on that modern hardware. As you crank up the load, look at what happens to Memcached. Its latency just skyrockets into orbit. That's the cost of all those threads fighting over locks. Now look at Sphinx. It's just a flat line. It stays consistently low, consistently stable, no matter how hard you push it. That is the shared nothing design just proving its worth in spectacular fashion. And this isn't some magic trick that only works on expensive, modern hardware. Check this out. Even on the older legacy machine with way fewer cores and a less capable network card, the thread per core architecture in Sphinx just runs circles around the competition. When it comes to read latency, Sphinx consistently delivers a lower tail latency. The performance advantage is fundamental to the architecture itself. And here it is, the headline number, the big payoff. In the absolute best configuration, that's the Sphinx shared nothing architecture, combined with that optimized IRQ affinity, the researchers measured a staggering 71% reduction in the worst case delays compared to a standard Memcached setup. Let that sink in. 71%. That's not just an improvement, that's a complete game changer. So this is a massive win, a huge leap forward. But it's actually not the end of the story. Like any good piece of research, solving one big problem reveals the next set of challenges we need to tackle to make our apps even faster. What's amazing is that this architecture is so efficient, it actually exposes new, deeper bottlenecks. That message passing we talked about in the shared nothing design, it works, but it creates its own overhead in software. And many of the more advanced networking tricks we'd like to use don't have good standard support in operating systems yet. And maybe the biggest one? Our network cards are getting so fast, they can now shovel data faster than our CPUs can process it. We need the hardware itself to get smarter and offload more of the work. And the researchers themselves sum this out perfectly. They say that the next big leap in performance isn't going to come from just software or just hardware in isolation. It's going to require co-design, a future where the applications, the operating systems, the CPUs, and the network cards are all designed from the beginning to work together as a single integrated system. And that really leaves us with a critical, fascinating question for the future of high-performance computing. We have squeezed absolutely incredible gains out of clever software architecture, as this research clearly shows. But as we start to bump up against the physical limits of what software alone can do, is the next great performance revolution going to be driven not by code, but by intelligent, programmable hardware? It's something to think about.